So our next part of the discussion in acids, bases and salts here is pH scale. This pH scale is nothing but it is a scale used to measure H plus ion concentration of acidic or basic solution. So if you go for this pH scale, here the pH means power of hydrogen ion concentration, of acid or a base, concentration of acid or a base. If you go for pH scale, this pH scale based on the hydrogen ion concentration, this pH scale is having lower limit, middle limit and the upper limit. So if you go for pH scale, this pH scale you can just take it like this. That is, it starts with the pH and H plus ion concentration. So here I am taking here, that is pH is 1, then H plus ion concentration is, if pH is 1, H plus ion concentration is 10 to the power of minus 1. If pH is 2, 10 to the power of minus 2 moles per liter. Then pH is 3, 10 to the power of minus 3. pH is 4, 10 to the power of minus 5. pH is 6, this is 5, this is 10 to the power of minus 4, this is 10 to the power of minus 5, this is 6, 10 to the power of minus 6, this is 7, 10 to the power of minus 7, 8, 10 to the power of minus 8, this is 9, 10 to the power of minus 9, this is 10, 10 to the power of minus 10, this is 11, pH is 11, 10 to the power of minus 11, this is 12, 10 to the power of minus 12, 13, 10 to the power of minus 13, and 14, 10 to the power of minus 14. Here when you take concentration, this concentration is expressed in moles per liter. Concentration, units of H plus ion concentration is expressed in moles per liter. So what you are noticing here is, that is, if you take, that is, from pH is equal to, from pH is equal to 1, so you can take here this as 0 if you want. You can take this as 0, this is 10 to the power of minus 0 also you can take. So from 0 to around 3.5, it is strongly acidic. The solution is going to become strongly acidic solution. From 3.5 to 6.9, 3.5 to 6.9, this is weakly acidic. If it is 7, then you can take this as neutral. The solution is neutral solution. from 7.1 to around 10.5 it is weakly alkaline. 10.5 to 14.0 it is strongly alkaline. So what are the applications of this pH scale? So you can just understand like this, that is, for acidic solution H plus ion concentration is always greater than OH minus ion concentration. For acidic solution, H plus ion concentration is always greater than OH minus ion concentration, and therefore the pH is always less than 7. Similarly, for basic solution, H plus ion concentration is less than OH minus ion concentration. That's why here pH is greater than 7. Similarly, for neutral solution, H plus ion concentration is equal to OH minus ion concentration. H plus ion concentration is equal to OH minus ion concentration. Therefore, pH is equal to 7. So for neutral solution, pH is equal to 7. For acidic solution, pH is less than 7. For basic solution, the pH is greater than 7. For acidic solution, you can take H plus ion concentration. H plus ion concentration expressed in moles per liter is greater than OH minus ion concentration, and for basic solution, the H plus ion concentration is less than OH minus ion concentration. That's why the pH is greater than 7. So the next part of our discussion in the pH scale is, that is, importance of pH in daily life. Importance of pH in daily life. First is all weak acids. For all weak acids, the pH is equal to, that is, 3.4 to 6.9. Example you can take, that is acetic acid, CH3COOH, acetic acid. Then you can take H2CO3, carbonic acid. This is carbonic acid. Similarly, all strong acids, pH is from 0 to 3.5. pH is from 0 to 3.3. If you take, then if that is the case, example, strong acids, you can take H2SO4. Sulfuric acid, you can take lime juice. You can take nitric acid. All these are strong acids. All neutral solutions, pH is equal to 7. For all neutral solutions, pH is equal to 7. We can take neutral salts like sodium chloride. Sodium chloride is a salt of strong acid and strong base. Strong acid and strong base, all neutral solutions. Similarly, all weak acids, all weak bases weakly alkaline. If you take, their pH is from 7.1 to 10.5. Example, milk of magnesia, in bracket magnesium hydroxide, in bracket, that is magnesium hydroxide, milk of magnesia. You can take weak bases means you can take ammonium hydroxide, is also the best example of weak base. Then if you want you can take aluminum hydroxide, ferric hydroxide. All these are the best examples of weakly alkaline bases. All metal hydroxides are weakly alkaline bases or weak bases. Similarly, if you go for strong bases, pH is equal to 10.5 to 14.0. So example, you can take strong bases means, example, you can take NaOH. NaOH is strong. NaOH is a strong base. KOH is a strong base. Barium hydroxide also, it is a strong base. Barium hydroxide also, it is a strong base. Actually, these strong bases, because the bases are strong, they release OH minus ions quite spontaneously compared to the weak bases. So strong bases, they have pH equal to 10.5 to 14.0. Lastly, for neutral solutions, for all neutral solutions, pH is equal to 7 already we have taken. So for example, illustrative, if you take blood is slightly alkaline. Blood is slightly alkaline and its pH is 7.1 to, its pH is 7.1 to 7.4, slightly alkaline. Blood is always slightly alkaline, it is from 7.1 to 7.4. Similarly, the fertile soil should have pH always equal to greater than 5.6, then only it is fertile. If the pH is poisonous, similarly tooth decay occurs if the pH is less than 5.5. So to prevent tooth decay, okay, a toothpaste with the more concentration of base in its composition is recommended. Its composition is recommended. So these are all some of the important applications of pH in our daily life. So we have studied variety of examples with different ranges of the pH scale. So we were able to classify the pH scale, the application of pH scale in the form of weak acids, strong acids, neutral solutions, weak bases, strong bases, and also blood. Blood is a part of pH scale. Fertile soil is a part of pH scale, and tooth decay is also a part of pH scale. Let us have some illustrative questions. Illustrative questions. First question: two solutions A and B have pH value, pH of 6 and 8 respectively. respectively. Which solution of A and B are acidic and basic respectively. Actually, you know very well that for solution A pH is 6 and for solution B pH is 8. So this pH is 6 is for acidic solution and pH is 8, this is for basic solution. Suppose if the question is which solution has more H plus ion concentration. One more question is framed. So what we can do here? Here for acidic solution, if pH is equal to 6, then H plus ion concentration is equal to 10 to the power of minus 6 molar. 10 to the power of minus 6 molar. If H plus ion concentration is 10 to the power of minus 6 molar, then according to Kw is equal to H plus ion concentration into OH minus ion concentration, where Kw is called ionic product of water. Here Kw is called ionic product of water, and its value is constant, which is equal to 1.0 into 10 to the power of minus 14 molar square. 1.0 into 10 to the power of minus 14 molar square. So for acidic solution, therefore Kw is equal to H plus ion concentration into OH minus ion concentration. So therefore that is Kw is 1.0 into 10 to the power of minus 14 is equal to H plus ion concentration. H plus ion concentration already we know. So because H plus ion concentration already we know, so we can take that value, that is going to be 10 to the power of minus 6 into OH minus ion concentration. So OH minus ion concentration is equal to 1.0 into 10 to the power of minus 14 divided by 10 to the power of minus 6. This upon simplification you are going to get 1.0 into 10 to the power of minus 8 molar. That means here for acidic solution, because for OH minus ion concentration is 10 to the power of minus 8 molar and H plus ion concentration is 10 to the power of minus 6 molar and OH minus ion concentration is 10 to the power of minus 8 molar. 10 to the power of minus 8 molar is less than 10 to the power of minus 6 molar. So for acidic solution, H plus ion concentration is greater than OH minus ion concentration. This is half part of the question is solved. Similarly, for a solution, for basic solution, pH is 8. If pH is 8, actually according to formula of pH scale, pH plus pOH is equal to 14. pH plus pOH is equal to 14. So here pH value is 8 plus pOH is equal to 14. So pOH is equal to, this is 6. If pOH is 6, then OH minus ion concentration is 10 to the power of minus 6 molar. 10 to the power of minus 6 molar. Therefore, again ionic product of water is equal to H plus ion concentration into OH minus ion concentration. 1.0 into 10 to the power of minus 14 molar square is equal to 10 to the power of minus 6, because H plus ion, because OH minus ion concentration, we already calculated 10 to the power of minus 6. Now we are supposed to calculate the H plus ion concentration. So therefore H plus ion concentration is equal to 1.0 into 10 to the power of minus 14 molar square divided by 10 to the power of minus 6 molar, which is going to be 10 to the power of minus 8 molar. So it is very clear that for the basic solution, the H plus ion concentration is 10 to the power of minus 8 molar, and for OH minus ion concentration is 10 to the power of minus 6 molar. I am circling both the values for this basic solution. For basic solution, OH minus ion concentration is 10 to the power of minus 6 molar and H plus ion concentration is 10 to the power of minus 8 molar. 10 to the power of minus 6 molar is greater than 10 to the power of minus 8 molar. That's why we can obviously say that OH minus ion concentration is greater than H plus ion concentration. So that means for a value of pH is equal to 8, for basic solution, always OH minus ion concentration is greater than H plus ion concentration. So the next part under our discussion in this chapter, that is acids, bases and salts, is more about salts and pH of salts. If you go for a salt, a salt is nothing but salt is always formed when an acid reacts with a base. Always it gives salt plus water. That means every salt contains small amount of acidic nature and small amount of basic nature in it. Every salt is made up of small amount of basic nature and small amount of acidic nature in it. For example, we take one example. For example, you take HCl is an acid, it's a strong acid, and base NaOH is a strong base. It reacts to give NaCl plus H2O. This is salt. But mind you, this salt of NaCl, it is a salt of strong base and strong acid. This is what you have to understand. So based on this illustration, now classification, broad classification. Broad classification of salts. It is divided into 4 types. That is, if you take salts are divided into 4 types. That is, salts, they are divided into 4 types. One is salt of strong acid plus strong base, salt of weak acid plus strong base, salt of weak base plus strong acid, salt of weak acid plus weak base. So based on this, I would like to give you some interesting examples. If you take the first category, that is first one, if you take salt of strong acid and strong base, if you take a salt, strong acid, strong base. We take NaCl, it is a salt of strong acid and strong base, so it will contain NaOH and HCl. It contains NaOH and HCl. It contains a metal, it contains a non-metal. You take potassium nitrate. It is a salt which is made up of It is a salt which is made up of, okay, I'll just take this as strong base, and this I'll take it as strong acid. Okay, KOH, potassium hydroxide, K, strong acid, HNO3, nitrate group. Like that, you can take as many number of examples as possible. That is, you can take even, for example, sodium nitrate, so sodium sulfate. So base is NaOH, acid is H2SO4 sulfate. That means here the salts, if you speak about the salt of strong acid and strong base, sodium chloride is a salt of strong acid and strong base. Potassium nitrate is a salt of strong acid and strong base. Sodium sulfate is also a salt of strong acid and strong base. If you take sodium chloride, if it is a salt of strong acid and strong base, sodium chloride is having strong base NaOH and strong acid HCl. Potassium nitrate is having strong base potassium hydroxide, strong acid nitric acid. Again, if you take salt, sodium sulfate is a salt, it contains strong base sodium hydroxide and strong acid sulfuric acid. So like that, you can go for the second category also, that is, if you take salt of weak acid and strong base, salt of weak acid and strong base, weak acid, strong base. So again, I'll take salt, weak acid, strong base. If I am taking CH3, I am taking CH3COO Na. This is sodium acetate. This sodium acetate contains weak acid, CH3COOH, acetic acid, strong base NaOH. So you can just take this as a salt of weak acid and strong base. If you want, you can take a sodium carbonate, potassium carbonate. You can take potassium carbonate. If you take, it contains weak acid, that is H2CO3 is the weak acid, and strong base is KOH, potassium hydroxide. So here we have potassium, here we have carbonate, here we have acetate, and here we have sodium, potassium carbonate. Like that, you can take as many number of examples as possible. That is, we can take sodium cyanide, HCN, hydrogen cyanide is a weak acid, sodium hydroxide is a strong base. So that means this is second category. So we can go for third category, that is weak base and strong acid, and fourth category, that is weak acid and weak base. Similarly, take the third case of the salts, that is weak base, that is salts of weak base plus strong acid. So you take salt, weak base, strong acid. Weak base and strong acid means you can take ammonium chloride, the best example. Ammonium chloride is the best example for weak base and strong acid. Weak base, so you can take ammonium hydroxide, weak base, strong acid, HCl. So it contains one ammonium group and one chloro group. Aluminium chloride, if you take, so you have aluminium hydroxide and HCl, aluminium chloride and HCl. If you take ferric sulfate, it's a salt of weak base and strong acid. So you have ferric hydroxide, it's a weak base, strong acid, H2SO4. That means here we have iron, and here we have sulfate, here we have aluminium, and here we have chlorine. So this is a salt of weak base and strong acid. So if that is the case, go for the next fourth case, last one, that is salts of weak acid plus weak base. So I am taking here, suppose take one example here, one example is sufficient for us to understand. You take CH3 COO NH4. It is a salt of weak acid and weak base. This is a salt. It contains, that is CH3 COOH plus ammonium hydroxide. This is weak acid and this is weak base. The salt of weak acid and weak base. Ammonium hydroxide, it's a salt of weak acid and weak base. So from this discussion we can make one conclusion. What is the conclusion we can make? All salts with the strong acid plus strong base, strong acid and strong base has pH is equal to 7. So they are neutral. These salts are neutral salts. These salts we can call them as neutral salts. All salts with the weak acid plus strong base, pH is greater than 7 and they are basic salts. All salts with the weak base plus strong acid, weak base plus strong acid has pH less than 7. So these salts are called acidic salts. Lastly, all salts with the weak acid plus weak base, again pH is equal to 7. They are again neutral salts. Salts of strong acid and strong base, they do not undergo hydrolysis. But salts of, that is weak acids and weak base, yes, they undergo hydrolysis, but the reaction is slow. Okay, reaction is slow and the endpoint is reached. Endpoint, of course, we can reach the endpoint, but the reaction is going to become slow here. And what we have to understand here is salts of strong acid and weak base, because the acid is strong. The salts of strong acid and strong base, because both the acid and the base, both of them are strong. That's why H plus ion concentration will become equal to OH minus ion concentration in the case of strong acid and strong base. That's why the pH of the salts of strong acid and strong base is equal to 7, and the solution is going to become neutral solution. The salt solution is going to become neutral solution. Similarly, salts with weak acids and strong bases, acid is weak, base is strong. So OH minus ion concentration is greater than H plus ion concentration for such salt solutions. That's why here the pH is greater than 7 and overall the salt solution is going to become basic solution. Similarly, if we take salts of weak base and strong acid, acid is strong, base is weak. So H plus ion concentration is greater than OH minus ion concentration. That's why the pH is less than 7 and the overall salt solution is going to become acidic salt solution. If you go for the salts of weak acid and weak base, both the acid and the base, both of them are weak. The weak acid will release H plus ion and the weak base also will release OH minus ions, but the interaction of H plus ions and the OH minus ions becomes very slow. The salt hydrolysis will definitely take place in the case of weak acid and weak base, but the reaction becomes slow and the end point reached in the salt of weak acid and weak base also it is very slow. That's why we can say that all the salts of weak acid and weak base also they can be considered as the neutral salt solutions. So the next part of our discussion in this chapter, that is acids, bases and salts, are, that is common salts, formulae, preparation and uses. Here the commonly available salts which are under our discussion is, that is, you can take here NaCl, NaOH, KOH, you can take Na2CO3, 10H2O, Na2CO3, 10H2O, CaOCl2, CaSO4, 2H2O, and NaHCO3. Of course, you can add one more, CuSO4.5H2O. Here NaCl we call it as simply table salt or rock salt, or sometimes even we can call it as sea salt. In aqueous solution, or sometimes in aqueous solution we can also call it as brine solution. NaOH, caustic soda. This is caustic potash. Na2CO3, 10H2O, we call it as washing soda. CaOCl2, it is called bleaching powder. Calcium sulfate 2H2O, this is you can take gypsum. NaHCO3, this is baking soda. Copper sulfate dot 5H2O, it is called blue vitriol. It is also called copper sulfate pentahydrate. Crystallized copper sulfate pentahydrate crystallized salt. Baking soda, this baking soda actually NaHCO3, if it is mixed with small amount of tartaric acid, it is going to become baking powder. So this tartaric acid, this baking powder, this tartaric acid, actually here this tartaric acid will supply the H plus ion. The H plus ion from the tartaric acid will be supplied to the baking powder. So what is the kind of necessary reaction taking place? Here if you take the necessary reaction, NaHCO3 plus H plus ion will convert the bicarbonate ion to carbon dioxide. It will convert to carbon dioxide, it gives Na plus ion, and also it gives H2O. This carbon dioxide gas allows the bread to swell and to become spongy. It allows the bread to swell and it becomes spongy and it gets expanded. It can be a bread or it can be a cake. So overall we can just take this mechanism as this is baking of foodstuff. Similarly, Similarly, if you go for gypsum, calcium sulfate 2H2O, calcium, once again I am trying to recollect all the salts one after the other. NaCl is sodium chloride. Sodium chloride is also called table salt or rock salt or sea salt or brine solution. So here, if you take, so we have just discussed about the baking of food in the form of cake or bread, and we have just understood the mechanism of how the baked food is going to swell and expand and it is ready for consumption. And if you take gypsum, if you take sodium chloride, so once again I am just repeating here, sodium chloride, we call it as brine solution. When sodium chloride is subjected to electrolysis to give various products at anode and cathode electrode, we generally term this sodium chloride as brine solution. But however, based on its availability in the nature, this most of the sodium chloride we try to extract or we try to manufacture from the seabeds. That's why sometimes it is also called a sea salt. And sodium chloride in the crystalline form, it looks of the crystalline rocky nature. That's why we call it as rock salt, and it is commonly used salt. That's why we call it as table salt. Sodium hydroxide is caustic soda. This caustic soda, it is actually manufactured, this NaOH, it is used in the manufacture of, it can be manufactured from NaCl aqueous brine solution. It can be manufactured from NaCl aqueous brine solution. And potassium hydroxide, of course, it is called as caustic potash. And sodium carbonate 10H2O, it is called washing soda. Sodium carbonate decahydrate, 10 water molecules, we call it as decahydrate, it is called washing soda. And this washing soda, it is an exothermic salt. It is an exothermic salt. That means if you take small granules of sodium carbonate, crystalline salt if you take, and if you just put it on your hand, and if you add some water, wet it and just rub it with your hands, then automatically you find that you can see the warmth nature of the salt. That means it is very clear that the sodium chloride, when it comes in contact with the water molecules, it generates heat. Because it is generating heat, the heat is released from the salt in the aqueous state. That's why this salt can be called as an exothermic salt. Go for bleaching powder. The bleaching powder, the chemical formula is CaOCl2. This can be read as calcium oxychloride. Calcium oxychloride, it is bleaching powder. We can prepare this bleaching powder, no problem, that we can discuss in the next part of the discussion. Gypsum. From gypsum, if you heat gypsum, on heating gypsum, we get plaster of Paris. On heating gypsum, we get plaster of Paris. And sodium bicarbonate, baking soda, and last one is copper sulfate 5H2O. It is also called as blue vitriol. It is called as blue vitriol. We call this as blue vitriol because the reason for we call it as blue vitriol, because you take copper sulfate solid, which is colorless. Again, when you add water in the liquid state, this water molecule, one formula unit, this copper sulfate, because it is a salt, we call this as formula unit. One formula unit of copper sulfate, when it is going to dissolve in 5 moles of water, then you get copper sulfate 5H2O. Once this copper sulfate, one formula unit of copper sulfate, when it is coming in contact with 5 molecules of water, it becomes copper sulfate pentahydrate. It gets crystallized. It is crystallized and you get bluish crystals. The blue color of the copper sulfate is because it is hydrated with the 5 water molecule. So similarly, if you take the NaCl uses, it is used in the manufacture of NaOH. It is used in the manufacture of sodium carbonate. It is used in the manufacture of sodium bicarbonate, and it is also used in the manufacture of bleaching powder. Say for example, if you take NaCl, if you are taking NaCl solid plus H2O liquid, you get NaCl aqueous brine solution. This NaCl aqueous is called, this is brine solution. It is called brine solution. So take this NaCl brine solution, subject it to electrolysis. When you are subjecting it to electrolysis, at anode you get chlorine gas. At cathode you get, at cathode you are going to get, that is at cathode you get H2 gas, and you also get, that is NaOH aqueous. Again, this hydrogen and chlorine in turn they react with each other to give hydrochloric acid aqueous. Now here this chlorine when it is reacting with NaOH, this chlorine and NaOH, when they are going to react with each other, both when they are going to react, here you get two products. Chlorine when reacts with the NaOH aqueous, we get NaClO, so plus H2O, so this is hypochlorite. This is cold, so you go for chlorine plus NaOH, 6 moles of NaOH aqueous. This is hot and concentrated, you get 5 moles of NaCl plus NaClO3 plus H2O. This is 3H2O. This is chlorate, sodium chlorate. Likewise, the chlorine which is obtained, one more I am going to give you. Chlorine when treated with the calcium hydroxide, that is dry calcium hydroxide, you get calcium oxychloride, CaOCl2, calcium oxychloride, CaOCl2 plus H2O. This is called bleaching powder. So this bleaching powder is used as a disinfectant for killing germs in water, germ-free water. Then the same bleaching powder, it is also used as a bleaching agent. In that is fabrics, paper industry, fabric and paper industry. So similarly, if you go for uses of chlorine, if you take, it is used in manufacture, it is used in the manufacture of CFCs. We call the CFCs as chlorofluorocarbons, and it is also used in plastic pipes, that is PVC. We call this PVC as polyvinyl chloride pipes. The pipes just looks like this. It's just like this. The pipe. This is the pipe. These are the long agricultural pipes which we use. These are the polyvinyl chloride pipes, PVC pipes. they are very tough and synthetic, tough and heat proof, and they are synthetic, PVC. And likewise, if you take NaOH uses, it is used in degreasing, okay, degreasing of metal surfaces, in soap manufacture, in textile, paper industry. Similarly, preparation of NaHCO3. Actually, you can prepare NaHCO3 by taking Na2CO3 sodium carbonate when treated with carbon dioxide gas and when treated with water in the presence of liquid gives rise to NaHCO3 solid. Balance the equation, take 2 over here. That means 1 mole of sodium carbonate reacts with 1 mole of carbon dioxide in the presence of 1 mole of water. Upon heating, you get 1 mole of baking soda. 1 mole of baking soda. So this is how we try to prepare the baking soda, and this baking soda, it's a good antacid to relieve pain in stomach. So good antacid, this baking soda is a good antacid. It is used to relieve the pain in stomach, and it reduces acidity, thereby bringing relief to the given person suffering from acidity. Gastrointestinal acidity can be temporarily relieved by taking this sodium bicarbonate as an antacid, and it is also used in the baking of foods because of the property, the sodium bicarbonate, it is unstable. So it gives carbon dioxide, it gives one Na plus ion, and also it gives one OH minus ion. So this carbon dioxide is going to play a very important role in the swelled or expanded foods in the form of baked foods, or that is the fast foods. Generally we try to consume in the metro areas. So the next part of the preparation of salts is preparation of washing soda and plaster of Paris. Actually, if you take washing soda, that is preparation. If you take sodium bicarbonate, you heat sodium bicarbonate, heat it, you get sodium carbonate plus carbon dioxide plus water, liquid. This is gas and this is solid, and this is also solid, of course. Balance the equation. Take this sodium carbonate solid and you add 10 molecules of water, liquid, subject it to crystallization. You get sodium carbonate 10H2O. This is sodium carbonate decahydrate. 10 water, no? So that's why we call it as decahydrate. This is in the anhydrous form, anhydrous or dry state. of the salt. So this is about the washing soda preparation. Now go for plaster of Paris. If you go for plaster of Paris, if you go for the plaster of Paris, that is, you take CaSO4, calcium sulfate solid, which is actually called as salt cake. This salt cake, calcium sulfate solid, when it is added with 2 molecules of water liquid, it is subjected to crystallization. So you get calcium sulfate 2H2O. This is gypsum. Calcium sulfate dihydrate, because 2 molecules of water are there. 10 molecules of water decahydrate, 2 molecules of water dihydrate. Gypsum dihydrate or decahydrate, dihydrate or 2 molecules of water. So take calcium sulfate 2H2O, you heat to a temperature of greater than 120 degrees centigrade or simply 373 Kelvin temperature. If you heat, then it will lose 1.5 moles of water, calcium sulfate half H2O plus 3/2 moles of water. This is called calcium sulfate hemihydrate. Calcium sulfate hemihydrate, and this is nothing but plaster of Paris. This plaster of Paris, it is used in false sealing, small false sealing in the manufacture of toys, groceries, dentistry, in taking the impressions of the jaws of teeth for a dentist, and also in repair of fractured bones of orthopedist. An orthopedist is a person who tries to give the prescription, who tries to heal or who tries to repair the bones, damaged bones. So these are all some of the important uses of plaster of Paris. And washing soda, it is used for washing purposes. Baking soda, it is used for baked food items. And these are all some of the applications of various salts which we have to learn here in this particular topic. End. So if you go for this plaster of Paris, if you take plaster of Paris formula, if you take CaSO4 half H2O we are taking, we can also write it as 2 CaSO4 of H2O. Also we can write the formula of plaster of Paris. This plaster of Paris, again, if you take this plaster of Paris CaSO4 of half H2O, if you add again 3/2 moles of water, this process we call it as hardening, and also we call this as setting. It involves 2 stages. POP, plaster of Paris, involves 2 stages, hardening and setting. So during hardening and setting, this plaster of Paris is again converted to 2H2O, that is gypsum. This principle, it is used in the preparation of casts, molds. These casts and molds are understood in the form of statues. They are understood in the form of, that is, statues. Casts and molds are understood in the form of statues. Cut.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.